Hello viewers, in this session we are going to look at some examples concerning Taylor's theorem, and then we will analyze the properties of zeros of an analytic function, that is the points where an analytic function is 0. Okay. And we will see some theorems concerning the zeros of analytic function. Okay. So, firstly some examples for Taylor's theorem. Okay. So, the first example is determining the power series of a function. Okay. So, to determine the power series of f of z equals z power 6 sin 3z. Okay, so, what we can do is we can actually use Taylor's theorem and say that the power series of this function f of z will equal whatever the Taylor's theorem says, the coefficients C n are given by the nth derivative of this function divided by n factorial, etc. But to compute the derivatives of this function is tedious. Okay. So, instead what we will do is we will compute the Taylor series for this function sin 3 z, okay, and then multiply by z power 6. That is easier than directly computing the Taylor series for f of z. Okay. So, we know by one way or the other that the Taylor series for sin 3 z, well, by using its derivatives, let us say the Taylor series. Okay. So, the Taylor's series for sin 3 z is sin 3 z equals sigma n equals 0 through infinity of minus 1 power n 3 z raised to 2 n plus 1 divided by 2 n plus 1 factorial. Okay. So, the Taylor series of sin 3 z, z being a complex number, tallies with the Taylor series in the real case for sin 3 x, okay, where x is a real number. Okay. So, x replaced with a complex number z here works. Okay. And the radius of convergence of this series is infinity. So, what this means is that for any z belongs to C. Okay. So, sin 3 z is this. So, we can say that f of z, the Taylor series for f of z is nothing but z power 6 multiplied by this Taylor series n equals 0 through infinity minus 1 power n 3 z power 2 n plus 1 divided by 2 n plus 1 factorial. Okay. And then take the z power 6 inside and multiply. You can do that because you have a convergent power series and z power 6 is anyway an analytic function. So, this is n equals 0 through infinity minus 1 power n. Okay. So, this is 3 power 2 n plus 1 times z power 2 n plus 7 divided by 2 n plus 1 factorial, okay, for any z belongs to C. Okay. So, this is much easier than actually finding the derivatives of f and then figuring out its Taylor series. Okay. So, this is a practical note, okay, as opposed to using the Taylor's theorem directly. Okay. So, now the next example is that of the logarithm, a branch of a logarithm. Okay. So, here is the example. So, consider the set complex plane minus the segment minus infinity is 0. Okay. So, this is not really, I mean, this notation is kind of sloppy, but you understand what this is. This is the complex plane minus the negative real axis including the point 0. Okay. So, you have removed the real axis along with the point 0. Okay. So, you consider this set. So, that is a branch cut and you can define a logarithm on this as we know from before. Okay. So, f of z define f on c minus infinity comma 0 as f of z is equal to log modulus of z plus I theta, where you constrain theta to be between minus pi and pi. Okay. And theta here is the argument. Okay. So, I should say theta belongs to log mod z plus I theta and theta is belongs to the argument, the set argument of z. Okay. Recall, argument of a complex number is a set, okay, and the entries are are at 2 pi apart from each other. Okay. So, if you constrain theta to be in this region minus pi to pi, then you have a function here f of z equals log mod z plus I theta. Okay. So, this as we know is a branch of logarithm. Okay. So, f is analytic on c minus infinity comma 0 as we know from before. Okay. So, f must have a Taylor series expansion locally at every point in c minus infinity comma 0. Okay, that is Taylor's theorem. So, in particular, let us pick a point here. So, on this complex plane on this picture, let us pick a point, let us say 1 on the real line. Okay. So, now we can expect this Taylor series for this branch of logarithm to have a Taylor's series expansion in a disk about 1. Well, how far can that disk stretch really? Well, that disk can actually stretch until we hit a point where the function is no longer analytic. So, we can expect this disk to have radius 1. Okay. So, this disk will have radius 1 and it is centered at 1. Okay. So, it is an open disk, remember. So, we can expand, we can hope to have Taylor's expansion for this, for f, I will say f, that branch of logarithm, okay, for f around the point 1, okay, around 1 with radius of convergence. Okay, and let us try to get the Taylor series expansion. Well, instead of finding the derivatives etcetera directly, once again we will resort to indirect methods. Okay. So, first we know that 1 by z, okay, the function 1 by z can be written as 1 by 1 plus z minus 1. Okay. And in this disk itself, in this disk under consideration, or the disk of our guess, this is equal to sigma n equals 0 through infinity of minus 1 power n modulus, or sorry, z minus 1 raised to n. Okay. So, this function has this series expansion, power series expansion, it is a geometric series as long as the modulus of z minus 1, this quantity, is strictly less than 1. Okay. This is I e in B 1 1. Okay. Z, I e z in B 1 1. Okay. So, we will actually use the fact that this function 1 by z is the derivative of log z on c minus on the domain given here c minus infinity 0. Okay. So, d by dz, since log z is analytic, okay, and its differentiation is 1 by z on the disk of interest, at least actually its derivative equals 1 by z on all of its domain. Okay. So, this is equal to sigma n equals 0 through infinity minus 1 power n z minus 1 power n for z belongs to B 1 1. Okay. So, we also know that the power series, if log z has a power series, if log z is equal to sigma C n z minus 1 power n equals 0 through infinity for z belongs to B 1 1. Okay. Then we know that d by dz of log z, okay, we saw that power series are analytic and their differentiation is given by differentiating it term wise. So, this is n equals 1 through infinity of n C n z minus 1 power n minus 1 for the same z, okay, for z in B 1 1. Okay. What this means is that by comparison of this and this, what we get is that n. Okay. So, I guess by shifting index, okay, what we get is n C n, okay, is equal to n C n is equal to minus 1 power n minus 1. Okay. And not only that, this is true for n greater than or equal to 1, okay, and f of 1 is 0. Okay, log 1 is 0. So, C 0 is 0. Okay. So, f of z is equal to sigma n equals 1 through infinity of minus 1 power n minus 1 divided by n, because C n is now from here C n is minus 1 power n minus 1 divided by n, okay, times z minus 1 raised to n for z belongs to B 1 1. Okay. So, that is the power series for this branch of logarithm. Okay. Once again, a little indirect way, we use the power series expansion of the derivative of this branch of logarithm to obtain the power series for the logarithm. So, another sort of remark really on Taylor's theorem. Okay. So, the function when we see the following function and its Taylor's expansion in the real case, i.e., the function 1 by 1 plus x squared as a function of real numbers, we see that its expansion is 1 minus x squared plus x power 4, etc. Okay. So, and then the radius of convergence happens to be 1. Okay. It is not immediately clear why this function 1 by 1 plus x squared should have a radius of convergence 1 when it comes to Taylor's series. Okay, and in the real setting, in the real number setting. But when we ascend to the complex number setting, we see that 1 by 1 plus z squared is 1 minus z squared plus z power 4, etc. Okay, with mod z less than 1, and we sort of see why this 1 acts as a barrier for this power series around 0. Okay. So, what I mean by that is around 0, you notice that 1 by 1 plus z squared is analytic on B 0 1, okay, but is undefined at plus or minus I. Okay. The numerator, the denominator actually becomes 0. So, I and minus I here actually act as a barrier for the expansion of power series around 0. Okay. So, this series really does not extend beyond this disk of radius 1. So, that is a geometric explanation of why the radius of convergence of power series 1 by 1 plus z of 1 by 1 plus z squared around 0 sort of has a radius of convergence 1 and it does not go beyond. Okay. So, this I and minus I, which are not points of analyticity of 1 by 1 plus z squared, act as barriers. Okay. So, a similar phenomenon we saw happens in the case of this branch of logarithm. So, beyond this radius 1, okay, we have points here. Okay. We have points here which are not points of analyticity of this function of this branch of logarithm. Okay. So, likewise, if we going back to this example, if we take let us say 10 on the real line, okay, or any complex number c for that matter. Okay. So, let us pick this example of 10 on the real line, then we can expect to have a power series expansion for this function, this branch of logarithm with radius of convergence 10. Okay. So, that sort of solves the quote unquote mystery of why these power series have a certain radius of convergence and why that power series cannot be extended forever beyond a point. Okay. So, these functions when they have certain barriers or points where they are not analytic, their power series expansion around certain points cannot be extended. Okay. So, that also we can note from Taylor's theorem, okay, and power series in the complex plane. All right. So, next what we will do is we will use Taylor's theorem to study the zeros of a complex analytic function. Okay. So, this is zeros of analytic function, okay, of an analytic function. Okay. Firstly, some notation. A 0 of a function f, like we know, okay, of a function f is a point a where, okay, f of a is equal to 0, that we call as a 0 of a function. Okay. So, let define z of f, we will use this notation. Z of f we will use this notation following the textbook of Priestley. Okay. Z of f is equal to z belongs to G such that f of z is equal to 0. Okay. It is the set of all zeros of the function f. Okay. So, Taylor's theorem actually gives us some important conclusions about the zeros, okay, and we will see that. So, suppose f is analytic on a certain BAR, okay, a ball of radius r around A, okay, r strictly positive, okay, and suppose that f of a is equal to 0. Okay. Then Taylor's theorem tells us that firstly, since f is analytic in the ball of radius r around A, okay, f has a power series expansion about A, okay, with certain radius of convergence. Okay. So, C n z minus a power n n equals 0 through infinity, at least the radius of convergence is r or is at least r. Okay. So, for modulus of z minus a strictly less than r, okay, where we also know that C n is 1 by n factorial the nth derivative of f at a. Okay. We also know that since f is 0 at A, C 0 is 0. Okay. Since f of A is 0, okay, f of A is C 0. So, now there are two cases. Case 1, if all the derivatives of f at A are 0. Okay. So, if all the derivatives of f at A are 0, okay, then Taylor's theorem tells us that then f is identically the 0 function, on BAR. Notice this is far from true for functions of real numbers. There are functions whose derivatives are all 0, but then the function itself is non-zero. Okay. So, since analytic functions have local power series expansions. So, since they are equal to a certain power series and the coefficients of this power series are nothing but the derivatives of f. If f is 0 at a point, then and if all its derivatives are 0, then the function should be identically 0 on that disk of radius r. Okay. So, that happens for complex analytic functions. So, that is a very important conclusion from Taylor's theorem, okay, about the zeros of a function. Okay. And then case 2, suppose that is not true. Okay. So, if all the derivatives of f at A are, if not all of them are 0, then there is a smallest positive integer such that the mth derivative of f at A is non-zero. Okay. So, if not, okay, if case 1 is not true, let m be the smallest positive integer, okay, such that f m, okay, the mth derivative of f at A is non-zero. Okay. Correspondingly, that particular C m in in the Taylor series expansion will be non-zero. Okay. Then what we can say is that f of z, by definition m is the smallest positive integer. So, f of z looks like z minus a power m sigma n equals m through infinity of C n now z minus a raised to n minus m. Okay. What I am doing is the expansion for f now starts at n equals m, okay, because C n's are all 0 for n less than m. Okay. So, I will start the expansion from n equals m, and when I start the expansion from n equals m, I know that I can factor out z minus a raised to m. Okay. And I do that, and when I factor out z minus a raised to m, what I get is this form. Okay. So, this particular form. Okay. So, this form, and now also I should immediately note that this is true for modulus for z belongs to BAR. Okay, did I use R? I guess I used R. Yeah. Okay. So, now what is also important is that with this is true with C m, okay, with the first term C m not equal to 0. Okay. So, so that is the Taylor series expansion. Okay. Then f in this case, in case 2, okay, in this case is said to have a 0 of order m at A. Okay. So, the 0 is called a simple 0, okay, if so this is 0 of order m, okay, at A, and then the 0 is called a simple 0 if m is equal to 1, okay, which means the factoring out occurs for, I mean m equals 1, that is the smallest integer for which the C n is non-zero. Okay. So, you see that from this thing circled in red, you see that f of z sort of behaves like a polynomial. We know that polynomials, if they have a 0 at a point, you can factor out that particular z minus a raised to a certain power m, where m is the order of 0 of that polynomial, okay, and then whatever is the remaining factor that is non-zero at that point a. Okay, you can factor out a polynomial that way. Okay. So, likewise you can factor out an analytic function locally, okay, in that fashion. So, in that sense the analytic functions behave locally like polynomials, okay, in that sense. And then what I want to say here is I want to take an example. Here is an example, sin z, okay, is equal to 0, we know for z equals k pi, and only for these values of z. Okay. And we also know that the differentiation of sin z is cosine z, okay, which is not equal to 0 at z equals k pi. Okay. So, we already see that the first derivative of the analytic function sin z is non-zero at the zeros of the analytic function. Okay. So, here so all the zeros of sin z are simple, because m in this case, okay, m in this case is just 1, the first derivative is non-zero. Okay. So, so that happens for sin z. Okay. So, that is an example of an analytic function which has simple zeros, okay. And it is likewise relatively easy to construct examples of analytic functions which have double zeros or triple zeros. What I mean by that is they have zeros of order 2, 3, etc. Okay. So, you just take z squared sin z, or you know z sin z has a 0 of order 2 at okay, has a 0 of order 2 at 0, okay, z has a 0 of order 2 at z equals 0. Okay. So, I will actually state the following. Here is a fact, okay, which you can prove easily, or by just using what we have done using Taylor's theorem. Okay. So, if f and g are analytic on BAR, and f of a is equal to g of a is equal to 0, okay, and if NF is the order of 0 of f at a, and NG is the order of 0 of G at A, okay, then the 0 of f times G, okay, at A has, firstly note that f times G will be 0 at A, because f and G are both 0 at A. Okay. So, the 0 of f times G at A has order NF plus NG, simply it is the addition of order. Okay. So, because of this fact, which can easily be okay, obtained from this form of expansion, okay, and multiplication of power series, okay, you can multiply power series in a certain fashion, okay, and then you can immediately conclude this fact. All right. So, from there I can say that z sin z has a 0 of order 2 at z equals 0, okay, or for that matter now I can construct a function having 0 of a certain order at a point. Okay. All right. So, that's a fact there. Okay. And now, I want to further analyze this thing that I have circled in red. Okay. What I want to conclude further is that I will define. Okay. So, let f of z. Okay. So, let f have a let f of z equal. Okay. So, from above that is easier, from above the same setup f of z equal z minus a power m sigma n equals m through infinity of C n z minus a raised to n minus m, okay, for z belongs to B A R positive, okay, where C m, the first term, is non-zero. Okay. So, now what I will do is define, I will take this part which is non-zero, okay, define phi of z is as phi of z is equal to sigma n equals m through infinity of C n z minus a raised to n minus m. Okay. So, first as noted above, I can conclude that phi of a is non-zero, right, because C m is non-zero. Okay. So, phi of a which is C m is non-zero, and also note that phi is a power series. Okay. So, define this for z belongs to B A R, okay, on the very same set. Okay. So, since phi is a power series function, we saw that power series are analytic. Okay. Since phi is a power series, in fact convergent power series, okay, on is a convergent power series on B A R, okay, phi is analytic by what we already know, okay, and hence continuous, at least continuous. So, that gives us an important conclusion that if phi of a is non-zero, okay, so there is an epsilon positive, okay, phi of a is non-zero means that phi of z is non-zero for a certain z in a neighborhood around a. Okay. So, that is a property of a continuous function. So, there is an epsilon positive such that phi of z is non-zero for z belongs to B A epsilon. So, there is a whole neighborhood around a where phi is non-zero. Okay. Now, this immediately tells us that f has a 0. So, let us go back to this form. Okay. Once again this form here was in red. Okay. So, f has a 0 of order m at a, okay, and whatever is remaining, okay, this is non-zero at any point around a. Okay, this function is definitely non-zero around a, and we just concluded by continuity of this power series that this is also non-zero around a, okay, around a neighborhood of around this or in a neighborhood of a. Okay. So, what that gives is that the zeros of f are actually isolated. Okay. What I mean by that is there is a small neighborhood around the 0 such that f is non-zero in that neighborhood. Okay. So, what we conclude is that, so we conclude that the zeros of f are isolated in this case. Okay. What is this case? This is case 2 we are dealing with. Okay. This is case 2. Okay. So, we will sum this up in the following theorem. Okay. So, this we will call as identity theorem after the textbook. Okay. So, suppose that f is analytic on BAR, R positive, okay, R positive, and that f of A is equal to 0. Okay. Then either of the two happens. Okay. Case 1, f is identically 0 okay, in BAR, or 2, that is, this is the case 2 we are working with. Okay. 2 I will write below 2, the 0 of f at A is isolated. Okay. That is, there is an epsilon positive such that the punctured disk B prime of A epsilon, recall what that is B A epsilon minus the point A itself. Okay. So, B A epsilon, B prime A epsilon has no other 0 of f. Okay. So, as a consequence of this, what we can conclude is that consequently, if A is a limit point of z of f, then f is identically 0 in BAR. So, I will briefly provide a proof of this consequence. What this says is that well, if A is a limit point of z of f, okay, so what that means is that every epsilon neighborhood, okay, so every B A 1 by n, let us say, okay, contains a 0 of f, okay, an element of z of f. Okay. So, so 2 can't happen, 2 cannot happen, which implies 1 has to happen. Okay. So, which means f is identically 0 there. Okay. So, next we will try to extend this theorem, this identity theorem, for beyond a disk. Okay. So, obviously, this is not true for the whole domain of analyticity. Well, if the domain is disconnected, or I mean if the region of analyticity of f is disconnected, because f could be constant, one constant on one component and another constant on another component. And so, you could have f not identically 0, but then you know, all the derivatives of f are 0. Okay. So, here is actually a good extension of this theorem. So, identity theorem, this is called the identity theorem, general form. It states the following. So, let G be a region. So, recall, a region is open connected set. So, the connectivity of G is essential here for this theorem. Okay. So, the proof, as we can guess, is topological hence. Okay. So, let G be a region, and suppose that F is analytic on G. Okay. So, assume that the set Z of F, i.e., the zeros of F, okay, of the zeros of F has a limit point. So, there exists a limit point in G. Okay. Then F is identically 0. In G. Okay. So, if there is a limit point for the 0 set of F in the region G, okay, then F has to be identically 0. So, the proof is as follows. Okay. So, first let E be the set of limit points of the set Z of F. Okay. So, E is the limit point set of the set of zeros of F. Okay. E is non-empty is given. Okay. We assume that the set Z of F has a limit point, which means E is non-empty. Okay. So, that is given to us. So, first we will note that E is contained in Z of F. Okay. So, first let A belong to E. We will show that A is in Z of F. Okay. Then for each n belongs to n, okay, there is an A n belongs to ball of radius 1 by n around A, okay, with A n belongs to Z of F. Okay. So, this sequence A n, since limit n goes to infinity of A n is equal to A, okay, by continuity of F. So, here is a note, the limit definition of continuity is in order here. Okay. So, please note that if there is a sequence converging to a point, and if a function is continuous at the point, okay, then the limit the limit of the functional values on this sequence has to converge to the value of the function at that point, as long as the function is defined etc., at that point and in a neighborhood of that point. Okay. So, if the function is continuous, of course, it will be defined. Okay. So, all that is true. So, that is the sequential definition of continuity. So, by continuity of f, the limit as n goes to infinity of f of a n is equal to f of a. Okay. But we know that f of a n is 0 because a n belongs to Z of f. So, this is a constant sequence 0 on the left hand side. This implies that f of a is actually equal to 0. Okay. So, this implies that a belongs to the set Z of f. So, if we start with a point in the limit point set of the set of zeros, then that point itself is contained in the set of zeros. So, E is contained in Z of f. That is the first note. Okay. So, then what I am going to show is that this set E is both open and closed in the region G. Okay. What that will show is that E is both open and closed, and if G is connected, there are only two sets which are both open and closed in G, namely the empty set and the set G. But of course, E is non-empty, which will give us that E is the whole set G. Okay. So, the set of limit points of this zeros of f is the whole set G, which will mean that f is 0 identically on G. Okay. So, that is the strategy. So, E first I will show is open. Okay. If A belongs to E, I will show that there is a neighborhood of A which is contained in E. Okay. Then by what we have just done, okay, by above f of A is 0, because E is contained in Z of f. Okay. Also by previous theorem, okay, there is an epsilon positive, okay, such that f of z is identically 0 on B A epsilon. Noting this consequence, consequently, if A is a limit point of Z of f, then f is identically 0 in B A R. Okay. So, we are using that. So, since A is in E, we should have by the previous theorem that f of z is identically 0 on B A epsilon. Okay. So, now since we know something about B A epsilon, epsilon positive. Okay. Now, since every point of B A epsilon okay, is a limit point, of Z of f, E contains B A epsilon. Okay. So, f is identically 0 and this set is an open set. So, identically 0 on this open set, and since every point of that open set is a limit point of Z of f, E contains B A epsilon. So, E is open. Likewise, we can show that E is closed. What is the argument for E is closed? If A belongs to the set G minus E, okay, then we will do this in two cases. Case 1, if f of A is non-zero, okay, then by continuity of A of f rather, okay, there is an R 1 positive such that f of z is non-zero for z belongs to B A R 1. Okay. And so, this implies B A R 1 okay, is not in the 0 set of f. So, it cannot be in the set E. So, B A R 1 is contained in G minus E. Okay. Second, if f of A is equal to 0, okay, then by previous theorem, since A is not the limit point, okay, A does not belong to E. Okay. So, A is not the limit point, okay, there is an epsilon positive such that B prime, okay, f of z is not equal to 0 for z in B prime of A epsilon. That is by the previous theorem once again. Okay. So, this tells us that this implies B prime A epsilon is disjoint from the 0 set and A is not in E. So, this implies B A epsilon is contained in G minus E. So, in either case there is a neighborhood around A which is contained in G minus E if A is not in E. Okay. So, this implies E is closed. Okay. So, E is both closed and open in G, and E is non-empty. So, from previous topological considerations we know that so E has to be equal to G since G is connected. i.e., the limit point set is the whole set G, i.e., f is identically 0 on G. Okay, so, that is the proof of this theorem. Okay. So, we will continue with this in the next session.